Okay, in a similar way to previous videos then, we are resolving this time at node G. Node G has these elements. So this is our node G. We've got GH to find. We know GC is 0.5. And we know that FG is 15/8. And we are looking for the force D. FG is in compression, so we will calculate GH and GD. So GD is going to be in tension. So GD is equal to, again, the ratio of 5/4. If you remember our 3, 4, 5 triangle, this is 4, this is 3, so this is 5. So that's the ratio of the lengths of the members, but also because they're vectors, it's the ratio of the forces in those members too. So 5/4 times 0.5 gives us 5/8, which gives us 0.625 kilonewtons in tension. Okay, so this is our value here. Okay, and similarly for GH, we have 3/5 times 5/8, which is the force that we just calculated here in GD. And we need to add to that our 15/8, which is our force in FG. Okay, so we end up with that's 15/40 plus 15/8. Let's make these all which is 3/8 plus 15/8, which gives us 18/8, which gives us 9/4, which is 2.25, and that is going to be in compression. So our GH then is 2.25, compression on the top. And these are all kind of making sense. You can always do a sense check, because I would expect all these members across the top to be in compression, all these members along the bottom to be, well, 0 here, but tension. So this is tension here. And then these to be in tension. Diagonal. This one may not be, because we've got a larger load here of 4, but we'll come on to that and see whether that flips, and that might cause JE to flip as well. So the next node we need to look at then is H. So considering equilibrium about H, we end up with this node H here, which has elements going to G and J, and also down to D. This is an easy one because we've got no diagonal members coming from this point H. So our HD has to equal 0, because there is no other load associated with that load. There's no load down at D that would introduce a load into that, and our HJ is going to be equal to our GH, which we've already established is 2.25 kilonewtons, or 9/4, whichever way you want to look at it. So this is 2.25 also. and that is compression as well. Okay, so any load coming compressing on H has to be balanced by another load compressing from J to H, so it's in compression. Okay, we will quickly do D while we're here, so we'll come down to D. So we're down here from H, we have this going up to J, this one going up to G, which is 5/8 in tension. This one across from here is 15/8 in tension. Therefore, let's have a look at this. Going vertically, this is 0, so our vertical component says that this here must be 5/8 in compression this time. That's interesting. Yeah, so this does flip and go into compression, so that's 5/8 compression, because this tension has to be balanced in the vertical direction by a compressive force. So that one's going upwards in tension, this one has to come down in compression, and that reduces this 15/8 then. So let's just write this all out so you can see what I'm kind of doing in my head. But sigma vertically, dj must equal minus 5/8 relative to dg, so that instead of being in compression in tension is compression, so that's 0.625 compression. And that results in dE then being our 15/8, which is this value here in tension, plus 2 lots of 5/8 in the ratio of 3 to 5. Okay, which is 15/8 plus 3/4, 30/40, which is the same as 3/4. So 15/8 plus 3/4 equals 21/8, which is equal to 2.625 kilonewtons, and that will be in tension, which again, yeah, no, that's right, that's in tension. So dE then is 2.625 tension. So we've got a compression up here, tension here, and then this is a tension here. Okay, and we will move on. Where will we go next? Let's come from the other side next. So in the next video we will start over at B, and we will work towards this. I don't want to go to E because I've got this complication of the 4 here. So I will jump, you could do it either way, it doesn't really matter, but I'm going to jump to B and work backwards from B in the next video.